Good afternoon and welcome to seminar here at Glasgow Caledonian University and to our online webinar. My name is Branka Dimitrijević and I will chair today's meeting. Our seminars and webinars disseminate outcomes of feasibility studies undertaken by the universities involved in our project, in collaboration with small to medium-sized enterprises in Scotland. Our project supports a collaboration on these studies that aim to develop innovations for more sustainable building design and refurbishment. The project is funded by European Regional Development Fund and Scottish Government CIC program. Just a few housekeeping points before I introduce our speakers. This is a big building, Buchanan House, where this seminar is taking place. So there is a possibility that a fire alarm could go off. If this happens, we will have to stop, but then later we will continue and you are welcome to rejoin us. And afterwards, we will also publish a video recording of this event on our website, so you can watch anytime later on. We plan to finish presentations at 1:30, and then our audience here and online will be able to ask questions. Online audience can use chat facility to ask questions. The event will close at 2 o'clock. If your questions were not answered until that time, then they will be answered by email by our speakers. So today's seminar title is Independent Verification of a Climate-Based Worldwide Building Energy Index. This is a feasibility study that was undertaken by Glasgow Caledonian University and IES Ltd. And we have two speakers today, Dr. Rohinton Emmanuel from Glasgow Caledonian University, Dr. Darragh Gleeson from IES Ltd, and also David McEwen from IES Ltd is here to answer some questions that you might have at the end. So our first speaker is Darragh Gleeson from IES Ltd, and I would kindly ask Darragh to come over here. Thank you.
Okay, I'm going to start basically by giving a quick description of what exactly is the Climate Energy Index and what the Building Energy Index is, and I suppose the calculations behind them. We're moving on then to how we tested the concepts in-house to verify whether it was actually a feasible and working concept, and I suppose further elaborate then on how we upscaled the Climate Energy Index to enable a comparison between the index itself and actual building energy figures. And then I'll pass you over to Rohinton, who will continue on with the rest of the presentation. The Climate Energy Index is really intended as a benchmark figure for the energy potential of a given climate. So what we do is, if you imagine, say, a 1 meter cubed box of air, how much energy is required to condition that air to make it comfortable? How much heating energy, cooling energy, and humidification energy is required to ensure that that air is comfortable for people? Once we have these figures for heating and cooling and humidity control, we can then graph those values across the year, and this gives us a visual feedback on specific aspects of that climate. So I suppose if we look at the chart we have here, this will be typical of, say, a cold northern hemisphere location. So if you follow the red line being the heating throughout the year and the blue line being cooling, you see that we have a long heating period with significant heat demand and humidification required. So a long dry winter and then a short but hot and humid summer. So visually you can very quickly get to know the climate that you're proposing to build in. Or this is purely climate based. There's no reference to a building at the moment. So it's just an idea of the likely energy usage of a given climate. And you see again for a few more locations between the northern and southern hemisphere, obviously the heating and cooling curves are flipped. But then in more harsh locations, we see that the peaks and troughs are more accentuated, and then in more temperate locations, it's a more gradual peak and trough for the heating and cooling demand. So, I mean, it not only illustrates visually the harshness of a climate, but also the duration of specific periods, be the heating period and the cooling period. So I mentioned at the start that the calculation is based on how much energy is required to make that 1 meter cubed box of air comfortable. So in order to quantify that, we needed to define a comfort zone. So the comfort zone that we worked with, it's an area that's defined on a psychrometric chart as an area bound by a PMV of plus or minus 0.5, a relative humidity of no greater than 70%, and a moisture content of no less than 0.004 kilograms per kilogram. Essentially, what we do is for each location that you want to devise the climate energy index for, the annual weather file for that location is taken, and on an hourly basis, based on the air temperature, the moisture content of the air, we can calculate how much energy is required to maintain that air inside this comfort zone. So viewing that on a psychrometric chart, you see the comfort zone is indicated in green, and the different psychrometric processes involved are illustrated there. So when the air temperature is too high, we need sensible cooling. If it's too humid, we have latent cooling. So basically, you can visualize all these processes on a psychrometric chart. Then, once you've created your climate energy index for a given location, you can then compare that across a series of locations around the world. So you can really see where your location sits in relation to other locations. It basically gives you an idea of the climatic burden. So we know, all climates aren't equal. There'll be far more energy usage in a building built in Alaska to a building built in, say, Los Angeles. And this is really represented on this graph, which shows how the climate energy index varies across a broad spectrum of locations, from very cold to hot dry to hot humid, with the temperate locations in between. It also, I suppose, identifies what proportion of the energy is attributed towards heating, cooling, and humidity control. Working in tandem with this climate energy index, we have the building energy index, which effectively takes the energy usage from a building that you want to analyze and expresses it in the same units as the climate energy index. So this allows you to really benchmark your building in the context of climate. So as I said earlier, all climates aren't equal. So if you want to look at an energy efficient building performing in a cold location, energy efficient building performing in a more temperate location, if you're just comparing kilowatt hours per meter squared versus each other, there's no real direct reflection of how the climate impacts on one. So you might see that the building in the very cold location has higher energy usage, but it could be a much better design. Just in reflection to the climate it's placed in, it has much more of a challenge to overcome. So what the building energy index does is it allows us to benchmark that building energy versus the climate energy, so that for buildings around the globe, we have some means of comparing them against each other. Another benefit of the building energy index versus, say, current compliance methodologies, so say UK compliance, where there's a rigid protocol laid out for how you have to conduct your energy analysis. You have to use specific profiles, you have to follow certain rules. With the building energy index, it's applicable to any type of building, and your building energy model that you're going to create is going to be as accurate as possible, not tied into a specific methodology. And from those figures for your building, we extract the energy data, and based on the size of the building and factors such as the occupancy in the building and infiltration rate, we use this to calculate a building energy index expressed in the same units as the climate energy index. I suppose I'll move on to now to describe the research we did in-house into the climate energy index and the building energy index. So, I mean, before we invested a serious amount of time into the concept, we needed to make sure it could stand up. So our research was involved in, is the climate energy index really a good predictor of building energy usage? So, by the rationale that building energy will vary with climate, we expected to see, if we graph the climate energy index for the same building across a series of locations, the building energy index should follow the exact same trend. If this is the case, well then it shows us that the climate energy index is a good identifier of potential building energy usage, being that the building energy index is based on actual energy figures taken from a model. We're also interested to see, would things such as internal gain distort the comparison between the BEI and the CEI, because the climate energy index is only based on your location on the weather data, whereas your building energy index has, features associated purely with the building, such as internal gains. So we expected possibly there would be a shift from what are the most benign locations on the climate energy index towards more cooler locations. Take into account that when internal gains are taken into account, some areas that perhaps didn't require cooling under the climate energy index may require cooling once building loads have been taken into account. Another area we were looking at was to see, does the building energy index really give us a reliable idea of whether a building design is a good design or not? So to achieve that, we created a series of test models reflecting poor, good, and what we term great design, and compared them against each other. So we'd hope to see that buildings of the poor design standard should always perform worse than that of the good design standard, which should always perform worse of the great design standard. And also we wanted to see, for the building energy index, taken across multiple climate zones, are the results still valid, or are there any areas where it stands out as not being quite applicable? So we created 9 test models in order to cover a variety of building types and building uses, because the building energy index is supposed to be universal, so it should be applied against any type of building, be it a large-scale commercial building, a educational building, or even a domestic house. We feel the index should be applicable across any building type. In order to achieve the analysis, we populated these 9 geometry models with the relevant templates from the UK NCM method, just so we had some series of benchmark data to put into these buildings. The buildings varied from small 5-zone house to 750-zone educational building and 120,000 meters squared large retail building. So we covered quite a broad scope of buildings. As I mentioned, for each of those 9 models we created one reflecting poor design, good design, and great design. So the poor standard design was really, I suppose, representative of maybe typical building of 15, 20 years ago. Not one that would pass, say, modern compliance methods in the UK at least. Then the good design was probably more representative of a typical building passing compliance, and a great building was a best case scenario building with very efficient plants, very tight air tightness, etc. To achieve these variations in design, we varied the glazing bias on the buildings, edited U values, it's at different levels of infiltration rates, each building had different internal gains, and as well system efficiencies were varied across the three design standards. So for each of those models and design standard, we ran it through the building energy index calculation across 14 different locations in order to cover the complete spectrum of locations around the world. So we had, cold continental locations, such as Fairbanks and Minneapolis, through to more temperate locations, then hot and dry locations, and hot humid locations, in order to identify, are there any particular climates that pose problems to the index, so that we can, I suppose, refine the concept further. This one is just a map indicating the locations that we used. The blue markers are the cold locations, the red markers are the hot locations, and the green represented the more temperate locations. So with 9 models by 3 design standards and 14 locations, we had to run this calculation 378 times in order to produce the data we required to interrogate it. What we saw when the results came out was that the BEI did tend to follow the same pattern as the CEI. So we were seeing, a higher BEI value in the locations where we see higher CEI values, and I suppose the shape of, when graphed across all the locations, the shape of the graph remained roughly the same. There were some areas where there were differences, but I'll point these out as we get to them. I suppose the difference, the areas where we experienced the greatest difference was in the poor building designs, and also in the more extreme climates, so in the more extreme cold and in the more extreme hot humid locations, we saw the greatest divergence between the BEI and CEI. Whereas for more temperate locations, they tended to correlate much more closely. Because of the fact that our BEI results across 378 buildings did tend to show very good correlation with the predicted results from the Climate Energy Index, we took that to say that the Climate Energy Index is really giving us a reliable indication of the likely climatic burden on a building. As we'd expected, as one of the, I suppose, goals of the research to look into was that we did see in a shift from the most benign location from what was given in the Climate Energy Index towards slightly cooler locations. This varied as a function of each building. So for the more densely occupied buildings with higher internal gains, we saw a definite shift towards cooler locations, whereas within the residential spaces, there was really no appreciable shift between the most benign location. So this is just a graph charting the Climate Energy Index in blue versus the results for the BEI and for a good design building and a great design building. So we see that for this particular building type, which was a small residential space, we see that the great design tends to follow closely the Climate Energy Index. So essentially the great design really does not have any greater demand for heating, cooling, conditioning energy than what we calculate as the benchmark for the climate. Whereas for the poorer design, we find that in colder locations, there's far more heating demand required. And looking at another type of building, a commercial office, we see on this type, we do see the left shift. So for with the Climate Energy Index, the areas with the lowest energy demand were, say, Los Angeles and Sydney. Whereas what we found when we analysed the building energy results, this shifted more towards cooler locations. So that it was something that we anticipated when we started the research, but it is something that I suppose can be quantified into the index going forward. So to sum up the results from that part of the analysis, the great designs consistently achieved a better building energy index than the good designs, and the poor designs consistently performed far worse than both the good and great designs. So as an indication of building performance, the BEI achieved what we wanted it to achieve. We found that the difference between the designs was most pronounced in the colder locations. I'd anticipate this is more down to the fact that the poorer designs had higher infiltration rates, and so there was a greater heating demand on these buildings, which was exacerbating the difference between the climate energy index and the actual building energy usage. In order to ensure a useful comparison between the climate energy index and the building energy index, since the climate energy index is calculated for a specific comfort zone, it was necessary to ensure that the energy figures coming from the building also corresponded to a comfort zone. So we used I suppose a slightly modified version of the climate energy index comfort zone in order to ensure that the results coming out for these buildings for the building energy index were a valid comparison. They needed to maintain within a similar comfort zone. What we found with the comfort check was that with the poorer designs and more extreme climates, we saw high failure rates in the comfort check. But this was really systematic of the comfort check that we used, in that CLO values were fixed, and it was difficult to control the mean radiant temperature in the model we were using. So for, I suppose, practical application of the index, there would need to be variation in CLO values and airspeeds in order to give a more, I suppose, realistic assessment of comfort in the space, instead of what was a rigidly fixed band in our assessment. We anticipated the divergences between the climate energy index and the building energy index for the more humid locations, being that the calculation we used to determine the building energy for the building energy index wasn't quite as psychrometrically accurate as that used for the CEI. So in the hot, humid locations, the building energy index figures didn't really accurately reflect the latent cooling and the associated reheat, and this is why the humid locations didn't follow quite as closely with the CEI as did, say, the more temperate locations. In order to, I suppose, further the analysis, with the BEI, it's essentially your building energy expressed in the same units as the climate energy index. So we asked the question, well, what would happen if you took the climate energy index and expressed that in the same units as building energy, so in kilowatt hours per meter squared? In order to do that, you would have to take the climate energy index for each location, and then for each building take the floor area and hours of usage, and work that value upwards into kilowatt hours per meter squared. So it's kind of a building weighted variation on the climate energy index. This then lets us to compare it directly with building energy, directly compared with kilowatt hours per meter squared, and also opens the door for non-psychrometric loads to be included, such as lighting gains and internal gains. When we express the building energy in terms of the same units as the CEI, we tend to scale down differences between the two indices, whereas by expressing the climate energy index as a function of the building will, I suppose, magnify differences between the two indexes. Okay. So as we work the climate energy index upwards from the building energy index, we tend to apply a scaling factor to this value in order to ensure, I suppose, we could compare the trends versus the absolute figures. So there's an example for, I suppose, a great design for one of our office spaces. Again, it shows pretty much the same broad correlation we had with the CEI and BEI, in that the building energy value tend to show its most benign energy usage in these in cooler locations, whereas the climate energy index figures tended to favor warmer locations. Looking at a residential building, though, that same difference isn't seen as much, and they both tend to favour the same locations. Even looking at, say, a large retail space, again, I suppose that left shift wasn't quite as apparent. Okay, I suppose moving back to that slide again, we do see for this locations such as Bangkok and Singapore, you notice that the blue line there, which is this modified climate energy index, tends to rise further because that's the more psychrometrically accurate calculation, whereas our building energy figures was used a more simplified calculation. That's why in those hot, humid locations we don't see the lines following the same pattern. Okay, that's me finished for my section.
Okay, I will now present the our own work, that is Glasgow Caledonian's work, is to independently verify what IES had found in terms of the usability of BEI and CEI. I'll say something about what we found and perhaps some direction for further work. So the aim of our activity was to look at the physical basis of CEI, which is the basis, and then to look at BEI itself. Then we compare these with other known indices. There are about 45 years worth of work on attempting to quantify climate burden. So to look at that, and perhaps given the scope of this index, it is intended for different climates, 14 different climates as Darragh presented. Look at the suitability and applicability of it worldwide, and as I said before, say something about future development potentials. So the approaches to CEI, as he said, is a quantification exercise of climate burden of the building. Since it is comparable units, we can therefore then compare them across the climatic zones. So what I did was to look at one of the first indices that began to quantify in a very qualitative way, if it's an oxymoron perhaps. That was developed by Mahoney in UCL in 1965, really. So early efforts. And then to look at various attempts at this so-called bioclimatic chart, a modification of what Darragh showed before, the psychrometric chart. Just to set the context for those who may not be familiar with Mahoney's chart, Mahoney attempted to look at 4 major variables and try to see how design could influence this. It's a ventilation, rain, thermal mass, and heating. And by combining what we now know as the totality of comfort parameters, that is air temperature, humidity, wind, and so forth, into these parameters, and he was trying to come up with design guidelines that would inform the climatic load. It would Mahoney's chart would look something like this. We just made a simple Excel chart out of this by giving in the climatic data and looking at what needs to be done in terms of the 4 variables. We could then begin to select some indices that needs to be fulfilled in the building. So those who would like more details, perhaps you could show this later on. But I would just want to say that the indices that Mahoney used, or the early attempts used, are not exactly the same as what CEI is doing. CEI is almost exclusively on the energy. As Darragh said, it's the amount of energy that is needed to condition this given mass of air. So it cannot be directly compared. So we need to modify it. And the modification that we did was, if you kind of recall the indices that we had before. Sorry. At the bottom of this chart in here, the indices that Mahoney had. What I'm trying to do here is to try and weight it according to their importance. These are the 6 indices Mahoney had, the 3 indices on ventilation and rain, and the 3 A indices on thermal mass and heating. I then began to weight it depending on how important this is. This is a subjective exercise, but it recognizes the fact not all indices are equal. So, on that basis, the formula at the bottom is the kind of attempted modified Mahoney's index. In other words, we are trying to equate, try as much as we can, equate these 4 variables, which are some are thermal, some are heating, others are ventilation, and so forth. I hope you see the logic in there. Right? And then we attempted to compare the CEI with this modified Mahoney's table. And the 2 graphs, on the one on the left, I'm not sure whether you could see, the R square is 0.18. That is CEI versus modified Mahoney's table in here. The one here on the right is CEI versus, sorry, I think I made a mistake. It is CEI versus modified Mahoney, but I excluded one station from the 14, that is Phoenix. And I'll say in a minute why Phoenix was excluded. And then it dramatically improves the correlation between the two. And perhaps the reason why this improves has to do with the difference in climatic burden caused by sensible energy and latent energy. Perhaps that is the reason. And what I meant by that previous slide, and to look at what is going on with Phoenix's climate. Here is Phoenix's climate plotted on a bioclimatic chart, the chart that's developed by Givoni in the 60s, 69. And each line here represents a month's data. And the letters represent what needs to be done to make this climate comfortable. DH, for example, is dehumidification, V is ventilation, and so forth. H is heating, IG is internal gain, and so on. It's up on the left side of the graph. As you can see, this is a climate with a wide variation in monthly climatic load. Some months need ventilation, the others need very strong heating. So it behaves like a proper temperate climate in certain months. In other months, it is more like a hot humid climate. This is a climate with 50 degrees temperature and 3% humidity. It's extreme. So this perhaps is a special case, and that perhaps explains why it was an outlier. When you take it out, the index performs much better. And this compared to 2 regular climates. So here is Glasgow, might not feel like a regular climate, and Sydney, traditionally considered a good climate. And even in the case of Glasgow, on left, you would see all the months have roughly the similar kind of load. They all need heating, some level. And for Sydney's case, the humidity levels are relatively constant. The curved lines are the isolines of humidity. So these are climates that you could say are more conducive to building design as opposed to Phoenix, which is an extreme climate. And that begins to explain why the index doesn't perform very well in extremes. Perhaps Phoenix shouldn't be there as a building zone. We then move to looking at BEI itself. As Darragh said before, there are 3 kinds of building they are looking at: poor, good, and great. These are explained before. And we tried to look at whether we could explain some of the variations in this, and then compare with a simpler building simulation software, because as I said, one of the aim is to see how good the index is. So we are using some other index, some other software, in this case DROP, to simulate and then say something about improvement. So the software we are using is a very simple parametric, very few zone kind of software called DROP, developed by originally developed in UT, University of Texas in Austin, and then subsequently developed more with in Lund. So using the four input variables, outdoor climate and average cloud cover and so forth, we take simple information from climate file and look at the cooling or heating energy needs of the building. Here are some of the comparisons of BEI results versus the building energy consumptions predicted by Darragh. Poor on the left, great, and then below is a BEI versus great, but excluding some of the buildings. The reason why we wanted to exclude some of the buildings and the combinations, if you recall from Darragh's presentation, there were 378 simulations. Not all of them would actually occur. You wouldn't do a same building that you normally do in Singapore, in Fairbanks, and you wouldn't call it great in both cases. So some of the combinations will not occur. So if you attempt to take away some of the combinations that are outlier, that will not occur in reality, the performance actually improves dramatically. I'm not sure whether you could see the R square at the bottom is 0.8. It is very good, the correlation between the two. So it's a good predictor of building energy use, especially for great buildings, which means the index is successful. That's what the index tried to do. It wanted to take that kind of good best practice buildings. It does predict it very well. And as I said before, some of the unaccounted variations are because it's an artifact of our simulation comparison. So what could then we do in terms of improvements? Here is BEI versus energy consumption for great buildings, but we exclude hot, humid climates. I'll say in a minute why we attempted to look at hot, humid separately. And if you recall in the previous 1.8, here the R square improves even more, 0.84. Perhaps the reason for the improvement is these climate, the excluded climates excessive load in terms of dehumidification, which we know from psychrometric is a very hard thing to solve. So if you look at then the BEI versus subcomponent, that is the sensible need of building, sensible energy need versus latent energy. On the left side, we have BEI versus sensible energy, and the right, its graph is BEI versus latent. And if I could read the R square on the left, for sensible energy, R square is 0.92 versus latent is 0.8. So you can see the index predicts much better the sensible energy need of buildings. And when you look at it, when I did the comparison, the overall pattern looks similar to what was shown before. So if you then remove this hot, humid climate building, that is buildings in Singapore and Bangkok from the sample, even poor buildings perform very well. The R square there is 0.9 and great buildings is 0.93. So they all perform very well. So perhaps the problem is with hot, humid climate. It was already recognized many years ago. Hot, humid design in hot, humid climates is problem because of the excessive importance of dehumidification. So what then can we learn in terms of going forward? CEI, as I said, is a very good match with previous attempts. So we know that previous attempts worked. So this is a good index, good predictor. The outliers can be explained by looking at the climatic load, the extreme nature of climatic load in, for example, Phoenix. Perhaps the improvement could be is to look at weighting sensible load and latent load slightly differently. Instead, even though they are all energy, perhaps it is to look at latent as a more important in terms of thermal comfort. We have to keep in mind it's also an artifact of the comfort definitions that are universally accepted. For example, we are using PMV. Now we know PMV is not a very good predictor of thermal comfort in hot, humid climates. There are other reasons for it being not so. In terms of further improvements, it predicts, as I said before, great buildings very well. But we perhaps have to also look at poor buildings. given the sort of universal aspirations of BEI and CEI, we need to look at the performance of poor buildings, because a vast majority of buildings in the world are probably in that category. So if you want a quick and easy method to predict their energy needs, ideally they shouldn't be built, but that happens a lot. So in order to predict the poor buildings performance, perhaps we need to look at other ways to weighting it. So one of the suggestions then is to somehow weight passive design standards into it. That is, naturally ventilated buildings, especially for hot humid climates, and use them in the weighting system. There are attempts to weight or include naturally ventilated buildings in global thermal comfort standards. For example, there is this adaptive standard. ASHRAE has 55/2004, which begins to account for naturally ventilated building. Perhaps now we can begin to look at the climatic burden imposed for such buildings by naturally ventilated means. Another maybe is to also weight the sensible load and latent load differently. I do not know what the different weightage is, but that perhaps is for further work. Thank you very much.
Thank you very much, Rohinton and Darragh. And we can now start our questions and answers session. So here next to Rohinton and Darragh is David McEwen from IES, who will also be able to answer your questions. Let me see if any questions are coming. Well, while we wait for questions, I have prepared a few, and we can start the session, but also audience here in the seminar room is welcome to ask questions. So the first question is for Darragh. Could you tell us more about the software used to validate building energy index?
Yeah, we use our own software, IES virtual environment. It's essentially the software we produce in-house for energy analysis. We also use for UK compliance, and it can also be used for ASHRAE PRM. It's become, I suppose, multiple uses in terms of building energy, but also lighting and system simulation. So I mentioned earlier that the psychrometric process we used in our energy analysis wasn't quite as accurate as that used in the climate energy index. That was more in relation to the fact we were interested in getting a bulk number of models out to get more data to explore then say limitations of the software. If we had taken say more time to set up the models, we could have produced a say more accurate representation of the humidity control.
We have the first question from our online audience from Tamer Gado. Is BEI and CEI are already integrated? Are they already integrated in IES VE?
I think I can answer that one. I think the answer is not at the moment. It is possible to calculate the CEI and BEI using the VE as long as you know what rules to follow. But it would be our intention within the next year or two to put something into the software to make it fairly easy for people to calculate the CEI for the climate and the BEI for the building in relation to the climate. So the answer is not yet.
Okay, here is a question in the audience. Please introduce yourself and tell us where you're from and then ask a question. Thank you.
Hi, Emma Morton from Strathclyde University. You've looked at the climate burden from different countries. I was wondering if you've looked at regional variability in the climate of that and then how that impacts maybe on national design standards.
Wasn't one we'd included in the research. We'd really just looked at covering a broad spectrum of different climates as opposed to looking at kind of more minute differences regionally. So, I mean, we're more interested in a global spread than investigating regional differences, but so it could be something useful for further testing of the concept.
Perhaps I can also add some. I think that's what I was hinting at when we said great buildings. Perhaps great buildings in these climates would be passively controlled buildings. So, yeah.
Okay. Well, another question from me. You mentioned, Rohinton, that there were problems with hot, humid climates and using this index. So how this index could be modified to be more effective in hot, humid climates?
Yeah, I think perhaps it is, to clarify, it's not a problem of the index itself. It is a problem of defining the comfort zone for hot, humid climates. There is great debate about PMV as a comfort standard for hot, humid climates. It doesn't work usually. So perhaps the way to do is to look at better thermal comfort standards for hot, humid climates. So that is beyond the index. It is at the level of ISOs and others, ASHRAE and others. And the other is to, as we discussed before, other is to look at what is great buildings in hot, humid climates. Maybe they are passively ventilated buildings. We know what is great buildings in other climates. So to begin to increase the reach of great buildings in other climates by taking into account best practices in other climates.
Thank you very much. There is one question from online viewer. Do you intend to look into how CEI can be integrated within sustainability assessment tools such as BREEAM and LEED?
That hasn't been one of our priorities to now, because obviously BREEAM and LEED are very much controlled by the USGBC and BRE, but we do have fairly good links with both of them. I think it's certainly something in the future that we'd like to see people pick up on, because it's easy to understand. It's a climate-based energy rating system for buildings. So it's one of the tools that people can use, whether it's for benchmarking, whether it's for compliance, whether it's for rating buildings. There's all sorts of applications for this. So I don't know if it'll be within BREEAM and LEED. We don't anticipate that anytime soon, but we can see quite a number of potential uses for this.
Okay. Here is a question in the audience. Please introduce yourself.
I'm Dr. Charlie Russell, Glasgow Caledonian University. This is on. My question is, can you use this tool with the climate change databases like UKCIP and the various ones around the world too? Given that a building's lifespan is probably going to be in excess of 50 years, and we know that there's going to be climate change, so current appropriateness may be fine, but 15, 20 years time that may not be the case. Maybe I'm a bit late arriving, that maybe was already covered, but just wanted to ask a question.
I don't think I mentioned it in the presentation, but that was one of the, I suppose, intended uses of the index, that so as a climate-based benchmark for your building, you can then use it to benchmark against, say, future predictions of climate. All you really need is that annual weather file, which there's more and more being produced based on different prediction methodologies. So yeah, it can be used to benchmark your building against future climate change.
But this, of course, might mean that in some climates, like this one, you might find that the building energy actually goes down. Whereas in other climates, you could find the reverse. So there will be some quite interesting things in looking at future climate compared to current climate.
Okay. Well, one question now again from me. What could be other applications for BEI? Maybe David, you can explain in more detail.
I think I've kind of touched on that already. I think there's 2 or 3 main applications that we can see. This is something that should be fairly quick and easy for people to do as part of their designs. So if, for instance, you're involved in design of schools across the country, then there's no reason why you couldn't apply this to all your designs. And it would give you a measure of how each building compares to one another. But then once it's in operation, as Darragh explained, you can customize the CEI. So it's actually possible, you know, with a little bit more development, for us to compare what's actually happened in a building after it's been built, whether it's in commissioning or whether it's a validation period, to see did that compare with what the predictions were for PEI. And then you can begin to draw some interesting trends from that as well. Of course, it could be used as a compliance tool. It's an energy compliance tool that could be adopted. It's a lot more straightforward. It's a simpler calculation than many of the applications that are currently being used, both in the UK and America, for instance. And it can be a building rating tool. So there's a number of applications for this. I think we've kind of proved with this research that it is valid. There's some issues that we need to take away for some climate zones to develop further, but in other climate zones, the more temperate ones, we're pretty much there with something that we can develop to a fairly good working tool.
No questions coming from the online audience or from the audience here. Here's one more question, please.
Hi, so how do you anticipate then that the design team would use this tool?
I think it's one of a number of tools that they can use. It's an energy tool, so it's not taking account of other things in the building design. It's not about materials, it's not about how close you are to transport routes or ecology. It's about energy. So people are just interested in benchmarking the energy performance of a building. If you're building a model in our software, or if this was in someone else's software, you could very quickly establish from your design model how the building compares to its climate. And then after you've done a few of them, you begin to understand whether that's quite a good rating, or whether it's something that perhaps needs a bit more work. So I would say that members of the design team would want to see, well, is the BEI, is that 2 times the climate, or maybe they set a target of 1.5 times the climate energy, and that would be their design standards. So it's something you could use right from the start, the same as you would with Part L or something like that, or Section 6. You know, but it's something that can be very quickly established at each stage in the design. And then, as I said before, after the building's complete and it's in operation, you can then go back and see, well, how the BEI is compared with the predictions. So it can be used at any stage in the design.
So how is that different from building control standards, energy predictions at the moment?
Because it relates directly to the climate that the building finds itself within. And I think you kind of hinted at that earlier. So you can bring it right down. If you've got the climate energy information for your town, you can base it on individual weather files.
Thank you.
Okay.
And it's not a standardized building, it's your real building.
We have a question from Carol Bitzwissel. How one can indicate building occupancy level within the index? Is that possible?
Well, the building energy index is based on a simulation model of your proposed design. So that model is going to take into account building occupancy, infiltration standards, and heating set points. All that will be fed into your model. So from this, the index pulls out the relevant data it needs from your thermal data. So building occupancy will be taken into account within the index.
Okay, thank you very much. We have a question here in the audience. Please introduce yourself.
Yes, I'm Eduardo Kruger. I'm a visiting researcher here at the GCU, and I'm very curious about the whole material here. And I wonder if you have some written work on it, because from the presentation I have a series of questions here, and I'm a bit in doubt. And another question is about how to use this. If it would be as simple as using a table with the index for a certain climate, or if I have to run a simulation, a complex simulation for this. So I'm not sure how it works.
Okay.
First one,
First
maybe
one,
I could say that
yeah,
the ball is really in our code. We need to publish this, so we will fairly soon.
Yeah. I think for the climate, we could probably work towards some tables that people could look up for individual weather files. But in terms of customizing it for your building, it would need a simulation.
Okay. So would you have some kind of report where we can have some more information about this kind of index?
I think you need to realize that this is still work in progress.
Okay. Right.
So basically what we presented today is what we've done. We haven't done any more than that. You know, obviously we're going to go ahead and do some more, and there'll be more information appearing over the next 12 months.
Okay. Thank
But
you.
at the moment, that's basically what we've achieved today.
You just want to significant.
Huh?
Here is a microphone. Please
Yeah,
introduce yourself.
I'm Bimal Kumar from Glasgow, Caledonian. You guys, IES, you have just got a paper accepted at the
We are right
the
to
Sydney,
for our BIPSA in Sydney in November, and it's going to be on this topic.
Right. So that's something that'll be out in the public domain soon,
Yes.
and hopefully within the next few months, there should be another journal paper coming out from the whole team. We can pass on the Sydney paper to you.
Okay. Do we have any more questions here in the audience? There are no questions coming from online audience. Well, do you have any additional comments about future work? Anything else that you would like to say about this type of software tool, about their acceptance by professionals, about maybe increased use or maybe not sufficient use, and so on? What are your views and what are your plans? How do you see these type of tools being further developed and used?
I think this, what David alluded to earlier, this benchmarking is a huge need, especially across the 14 or so climate zones. We have in this country decent amount of benchmark, but it is not there across the world. In Phoenix, for example, there is no benchmark. It's nothing in Bangkok. So that could be a major use, because a simple way to kind of convert this into across climates would be very useful, so that designers know what to aim at. Second, I think, is this climate change. I think we need to perhaps link it to climate change more explicitly now. Maybe we will do that in the paper. This is very simple. All you need is a typical weather year, and we know how to make it from UK CIP's predicted climate. So this could be very easily done, maybe not by us, but we could say how it could be done in a paper, which could enable future designers and policymakers to set the benchmark at the right level.
I think I would add that the reason that we have proposed the CEI and BEI is because there are a lot of rating systems already in the world. Most of them are quite different. They can be very complicated. Very often people don't do them at the start of the design. They do them simply for compliance. So we ask ourselves, are they actually achieving what they're setting out to achieve? In some cases, I'm sure they are. In other cases, I'm sure there's missed opportunities. So one of the main drivers, to do this is really to give people a tool that hopefully is simpler, that they can understand, their customers can understand, and they can use at any stage within a building's design. They can use it for future climate, they can use it for buildings in operation. And, hopefully it can be used for compliance and other purposes. So that was really the reason for doing this, was to try and give people a different type of tool that they could use to make a difference.
Okay. Here is one question from Tamer Gado, who is a lecturer at University of Dundee. And he is asking, is IES interested to start another Kick-Start funded study? Well, I can add here that there are some rules about eligibility. The funders this is information for everyone. The funders of our project really wanted to encourage as many companies as possible to apply. So they limited the number of applications submitted by one company. So the rule is that during our project, a company can apply only once for feasibility study. However, another funder is funding academic consultancies, and they say a company can apply every year. So theoretically, IES could apply for academic consultancy every calendar year. Maybe this is a hint to contact Tamer Gado and see whether University of Dundee could offer any other assistance, and maybe some. And we have here answer from Tamer, yes, please. So, well, that's another success, establishing links between academics and different universities, which is also aim of our project. Do we have any more questions here related to these topics? Any dilemmas, any thoughts? There are no questions coming from audience. So it seems that if our speakers don't have any questions or anything else to say, we will finish our event a bit earlier. However, before we finish, first of all, I would like to thank all our speakers, to thank our audience here and our online audience, and then to remind everyone that our competition for feasibility studies and academic consultancy is open, and the next submission deadline is 13th of May. And we still have 34 awards to give for feasibility studies and 11 for academic consultancies. If you have any questions related to how to apply for feasibility studies or academic consultancy, please do contact me. The next seminar and webinar, its title is Solar Wall Systems for Domestic Heating, an Affordable Solution for Fuel Poverty. And this was a study that was undertaken by Professor Sue Rowe and Dr. Fan Wang of Heriot-Watt University and Nicholas Heath of ChangeWorks. It will take place on 6th of May, again at lunchtime. I would also like to remind you that it is possible to sponsor our events. So if you are interested in sponsoring any of our seminars or webinars, please do contact us. Thank you very much for watching. Thank you we look forward to receiving your applications for academic consultancy or feasibility studies, and to welcoming you again on 6th of May. Thank you.